Welcome to the Fairbanks Museum Earth Science Lab. My name is Michael, and today we're going to be working with hydrogen. We're going to be doing two experiments to find hydrogen. So this element, hydrogen, is the simplest, lightest, and most common element in our entire universe. So if you've ever seen the periodic table of elements, you know that there are very many different simple atomic structures that are the building blocks for every single thing in our entire universe here on Earth and then also far out into outer space. 75% of all the stuff on Earth and way out there in the universe is all hydrogen. That's how common this element is. For instance, our sun is made up mostly of this element, hydrogen. Hydrogen was formed during the Big Bang, that first event in our universe that created and sent around all of the elements, all of the basic materials that we know about today. So hydrogen is very common, very important, but it's very difficult for us humans to encounter it, to find it in our daily lives. Even though 75% of the whole universe is hydrogen, there is very little hydrogen in our atmosphere, in our air we breathe, and you will never find pure hydrogen unless you make it yourself and prove to yourself that you've made it. Hydrogen is invisible, has a particular smell, and we are going to do two experiments today where we are going to isolate hydrogen. What I mean is that we're going to take material that we're more familiar with, like water, and pull out the hydrogen that's inside of it. You've probably heard before that the chemical compound of water is oxygen and hydrogen, right? H2O. Water is two oxygen atoms attached to one hydrogen atom. We are going to pull that hydrogen atom away from the whole water molecule in order to get just the hydrogen atom alone. So this is something that you don't find happening all around you in your everyday life. You have to sort of force it to happen inside of a lab. So that experiment with water is going to be the second experiment. The first, we're going to pull hydrogen out of hydrochloric acid, or people call it muriatic acid. I'm going to start with this experiment because it's a little bit more exciting, it's a little bit more fun. Hydrogen is incredibly flammable. It's one of the most reactive elements in our universe. And that means that if I introduce it to a high energy flame, it's going to combust very quickly. If you've ever heard of a hydrogen bomb, you'll maybe understand how devastating, these kinds of reactions can be. Also, if you've ever heard of the Hindenburg disaster, it was a very large blimp filled with hydrogen that exploded. So we're not going to do anything that dramatic today, but we are going to make some explosions here in just a moment. So I'm going to set up for this first experiment, explain how it's going to work, and also we're going to use the reaction equation to understand exactly what's going on with this chemical reaction that we're going to create. So you'll see that in just a moment here. So before we get underway with our experiment, I want to use this reaction equation here to explain to you exactly what you're going to be seeing. So this equation works a little bit like a basic math problem, and it uses the chemical names for the different elements, the same that you would see on the periodic table, to show how they might mix or change or separate during any chemical reaction. So this kind of reaction that we're going to start with using hydrochloric acid and zinc is what we call a single replacement reaction. That means that when I take my zinc and my hydrochloric acid, certain elements between those two materials are actually going to change places. And we won't necessarily be able to see those very small molecules splitting up and rearranging themselves, but we are going to see really the result of those changes. So this arrow here is showing the actual process of the chemical reaction. We are going to see a little bit of boiling, a little bit of bubbling, a little bit of color change in the acid, color change in the zinc. And through that chemical reaction, we are going to change solid zinc here. Zn is the chemical symbol for zinc. And hydrochloric acid, which is 2HCl. The H is, of course, the hydrogen that we're trying to isolate. The Cl is chlorine. We're all familiar with chlorine as an element. It's something that we use in our pools to clean water or to sterilize water. And hydrochloric acid reacts with zinc and actually dissolves that zinc. So I'm sure that you've seen sugar or salt dissolve in water so that you take a solid, like a salt crystal or like zinc metal, and you can watch it basically disappear into a liquid. Of course, it doesn't actually disappear, it's just mixing together completely with that liquid. That's going to happen here in our reaction. And the result on the other side of this arrow, we're going to come out with ZnCl2, which would be zinc chloride. What's going to happen is the zinc is going to dissolve and mix with the hydrochloric acid, and we're going to get, really, it's a solid, it's an aqueous solid zinc chloride, meaning that we won't be able to see it right away, but that zinc is going to attach to the chlorine in the water, and it's going to kick out the hydrogen that was attached to that chlorine. So, if you see over here on this side, hydrochloric acid is hydrogen, H, attached to chlorine, Cl. Once the reaction takes place, zinc, Zn, replaces that hydrogen, and now the zinc is attached to the chlorine. As a result of the zinc kicking out the hydrogen is going to become a gas, and we'll actually be able to see it boil out of our solution and become hydrogen gas. Now, if you remember from the beginning, I mentioned that hydrogen gas is the lightest element. It is the lightest thing in the whole universe. So, we're going to try to capture that hydrogen gas as it tries to float up out of our beaker here. And also, if you remember, hydrogen is incredibly reactive, incredibly explosive. The way that we're going to show ourselves here that we did get hydrogen, that we isolated this hydrogen, is we're going to cause it to react. We're going to make it explode, basically, by using a match. So, now that you understand exactly how this experiment is going to work, I'm sure you're excited to see it in action. Here's our beaker. Here are some hot dip galvanized nails. These are very common things that you can find in the hardware store. These are basically just steel nails with a very thin coating of zinc on the outside. They're literally dipped in molten zinc. The reason that they do this is zinc doesn't oxidize, it doesn't rust. So these nails, as long as they have this little zinc coating, they're basically rust proof. What we're going to do is dissolve that zinc coating. here are some nails that I have already used in this experiment a little bit earlier, and you can see that there's no zinc left on these nails. These nails are shiny because there's zinc on them. These nails are dull because it's just the steel underneath. So, quite a few nails going into my beaker here, and now we're going to add our hydrochloric acid. Yeah, I can already smell it. Wow, got in my throat a little bit. So this is not pure hydrochloric acid because that would be dangerous. This is only a 34% solution, which means it's 34% hydrochloric acid cut with water. Wow, it smells vile. So, I want you to watch carefully as I take this hydrochloric acid and put it into our beaker. Very quickly, you will see those zinc nails begin to react with the acid. All right. Wow. Can you see all the boiling there? If you actually saw some of that gas escape just then before I put the stopper on, that was the hydrogen gas already beginning to escape. This reaction happens extremely quickly, as you can see. So, hopefully you can tell with the camera that those nails are still releasing a little bit of hydrogen gas. Most of this reaction happens just at the beginning, but you should be able to see the bubbles that are still coming off of those nails in there as that zinc strips away. Now, we've been collecting hydrogen inside of our beaker here for 45 seconds now, maybe. I'm going to remove the stopper, and I'm going to put a match right into the mouth of the beaker. What this is going to do is as the hydrogen now escapes the beaker, it's going to come in contact with the flaming match, and we'll have a violent reaction. Okay, hopefully you at least heard that and saw some of the flame. It also smells very funny. Yeah. So, maybe I'll show you this again one more time to see if I can again get a really good flame, a really good reaction. But that sound that you heard, that pop, and hopefully a little bit of flame, that was, you can see some ash floating here. That was the hydrogen very quickly exploding. That little bit of hydrogen. Okay, let me show you one more time. Okay, fresh nails in here. We're going to put our hydrochloric acid in now. And very quickly cap ourselves off here. Now, I'm actually going to hold it because this is reacting very quickly, and a lot of that gas is escaping. Okay. Now, if we trapped enough hydrogen gas in here, we could actually cause this beaker to explode when we light it. The reason that I'm not pushing the cork all the way down is that the expanding hydrogen gas in here would pop that cork straight out. We don't want that to happen because we want to capture the hydrogen. Now, let's light it again. Did you see the flame inside of there now? So this time it made less of a loud noise, but I at least, saw a column of flame in the beaker for a couple moments. So that's the evidence for us that we did isolate the hydrogen that is in this hydrochloric acid. Zinc and chlorine don't react violently with heat the way that hydrogen does. So we can pretty much be certain that we did, in fact, find and explode hydrogen in this experiment here, because it's the only part of the whole experiment that would have reacted like that. Now, before we get started on our second experiment here, I'm going to leave my beaker like this for a couple days until all of the water in here dissolves. What I'll find in a couple days, once that happens, is that the whole bottom of my beaker here will be filled with a very fine white powder. That is the zinc chloride that we made through this experiment. It's an aqueous solid, meaning that it is dissolved thoroughly in the water that's in our beaker here, in that hydrochloric acid mix. But in a couple days, we'll be able to see it as a solid. It's kind of the same thing that you could see if you take salt water and leave it out for a couple days so that all the water dissolves and all of the salt is left over. That's one way to show yourself an aqueous solution in action at home. So our first experiment was a violent single replacement chemical reaction. This experiment, we are also going to be isolating hydrogen, but it's not going to be quite as violent or sudden. This method of finding hydrogen takes a little bit longer, but as a result, it's actually quite a bit more useful for humans. If you've ever heard of people with the idea that in the future all of our cars will be able to run on hydrogen fuel cells, this is what they're talking about. We're going to build a hydrogen fuel cell here that very slowly separates hydrogen from water. So it takes that H2O molecule and rips the H's away so that all you're left with is O2 liquid and a very, very efficient fuel as hydrogen. So in the future, if we are able to build cars that can run on hydrogen fuel cells like this, all that you would need to do is when you go to a gas station, you fill up your fuel cell tank with water, and all that will come out of your tailpipe will also be water and this O2 liquid that we're going to create. So, in order for a hydrogen fuel cell to work, we are going to have to create a type of reaction called electrolysis. And what this means is we're going to make a reaction that's caused by electricity. So it's a chemical reaction, meaning that the actual atoms that make up the molecules in our experiment, which is going to be water, those atoms are going to change positions, move around as a result of an electrical current. So, again, we'll start with our equation here. In our electrolysis reaction, we're going to start, of course, with water. So here's my glass of water, but this isn't just water. In here also is a little bit of salt, a little bit of sodium. The reason that we have to do this is that salt turns our water into an electrolyte. You might have heard of an electrolyte if you've ever had Gatorade before. That's electrolyte water. All electrolyte water is water with a slight electrical charge. You can do that by putting many different many different elements mixed with water, cause that water to have a very slight electrical charge, and electrolyte water, can help you to hydrate better. But here, our water is an electrolyte so that it can react when we introduce another electric charge into the system here. To do that, we're going to use just a little 9-volt battery here connected to these two carbon rods. These are going to be the anode and the cathode of our experiment. They're both going to go into this water and attach to the battery. One of them is going to be attached to the positive end of our battery, and so that cathode is going to be positively charged. The other, our anode, is going to be negatively charged, and as a result, when they're both in this electrolyte water here, a current is going to pass between them. And as that current passes between them, on the negative side, on our anode, it's going to even out the charge of that electrolyte water. And when that happens, we're actually going to split those water molecules apart so that the O's, the oxygen, separates from the H, the hydrogen, which is what we want. So simply by passing an electrical current through our water, we're going to take H2O, or in this case, we have to think about it as two water molecules, two H2Os. When we charge them, they're going to split apart so that we get two H2s, two hydrogens, or really 4 hydrogens, to every 2 oxygens that we get. So this is a simpler experiment than our last. All that we're doing is we're really splitting water molecules. Okay, so let's get this started. So it took me a moment to set up my anode and cathode here, but now they're both attached to my 9-volt battery. And this carbon rod is my anode. That's where the negative electrical charge is right now. And you can see right now that it's evolving all of this hydrogen gas. You can see how all of the water around that carbon rod is boiling, essentially. You can see all of those small bubbles pulling off of that rod. Let me try to move this so that you get a better view of that. Oh, give it a moment to restart. There you go. All of those small bubbles there, that's all hydrogen gas. Those are all of the hydrogens that were, just a moment ago, attached to the oxygens in this glass of water. So this is something that you never see happening out in nature. Water molecules splitting apart, separating into hydrogen and oxygen. But right now I'm actually creating so much hydrogen here that you can really smell it. It's very strong. It smells a little bit like chlorine in a pool almost. So this isn't enough hydrogen gas right now to run a car or something like that, or even light with a match. But you could imagine this same setup in a very large tank inside of your car that's cranking out hydrogen. And that hydrogen is being pumped into the engine block of your car, where the explosive power of this very reactive hydrogen is used to move the pistons and drive your car. So it's a very exciting idea to have a hydrogen fuel cell like this run your car, because it's very cheap. All that you would need is water and, of course, a battery, which your cars already have and can charge freely from the car itself. But the problem with these fuel cells is that, of course, if you take a large package of hydrogen gas, and if anything happens to it, if your car gets in an accident and that fuel cell crumples, it could cause a really terrible explosion. It would be just like a hydrogen bomb or the explosion of the Hindenburg blimp. So this is really fascinatingly high-tech stuff that people are very excited about. But at the same time, we have to be careful with any new technology like this because it could be quite dangerous. So today we did 2 experiments where we isolated hydrogen. We pulled hydrogen out of the places that we can find it in our natural environment here, whether it be from water or from something like a hydrochloric acid. But there are other experiments similar to these that you can do at home. In fact, ones that are even more complicated when you look at them from the chemical side of things, when you really start to look at how those molecules and elements are changing in a reaction. So we were looking at our reaction equations before, and here is a more complex equation than either of the 2 that we looked at earlier. This is a double displacement reaction that also has a decomposition part to it. And as you can see, it is there's quite a bit more going on here, but this is a experiment that you can do at home. This is the really kind of classic baking soda and vinegar experiment. So by combining these two very common household items, you can create a pretty interesting and powerful reaction, but not a dangerous reaction, that has quite a bit going on at the molecular level, chemically. When you mix these two, the baking soda and the vinegar, you are really swapping around different elements and causing molecules to decay and fall apart. Unfortunately, we can't see all of that with the naked eye, but as a result of a complex molecular reaction and change, we can see very visible results. When you mix baking soda and vinegar, depending on how much you're mixing together, you can get a very strong reaction. So I encourage you at home to try out this experiment and also others that you can find online. The two experiments that I did today are not ones that you should do in your house unsupervised or even with your parents. Hydrochloric acid is something that is dangerous. You shouldn't get it on your hands, certainly not in your eyes or anything like that, and you also don't want to be exploding large amounts of hydrogen anywhere in your home, of course. So I encourage you to go out and try household experiments like this, but just make sure that you are being safe when you do so. So thank you very much for tuning in to the Fairbanks Museum Earth Science Lab today. Again, I'm Michael. Thank you very much.